So last time we were talking about how we could potentially identify synchronization-free parallelism, and we're going to continue that discussion in this module. So in particular, we're going to talk about affine space transforms and affine space partitions. And to understand what I mean, let's look at the example that we also looked at in the previous module. So I have this program for I equals 0 to 1000, for j equals 0 to 1000, aij equals ai plus 1, j minus 1. Now I want to point out that, in this example, I'm just assuming that a of minus 1 is also a valid memory location and things like that. So don't worry about that. And I said that, look, this program does not look like it is embarrassingly parallel because there are data dependencies across different dynamic instances of the same loop nest. And in fact, there are two different accesses. So there are dependencies, data dependencies across the two different accesses. Within the same access, perhaps there are not any data dependencies, because if you look at it, every time each access is going to access a different element. Although there are data dependencies across different accesses. Now he said, but even though it's not embarrassingly parallel, it's possible to transform this loop in such a way such that we are able to extract at least some amount of parallelism. And the transformation is for k equals 0 to 1998, for L equals 0 to minimum of k comma 1999 minus k, a k minus L comma L equals a k minus L plus 1 comma L minus 1. And we say that, look, this basically program is data parallel on the first loop, which is the top level outer loop. But the inner loop is not data parallel. So there are dependencies across the inner loop, but there are no dependencies across the outer loop. Now, how do I claim that? How do I know that there are no dependencies in the inner, across different iterations of the outer loop, whereas there may be dependencies across different iterations of the inner loop? Well, one way is to basically, in this particular example, because it's only a 2-depth loop, I could draw a diagram like the way I had drawn in my previous module and show that indeed the inner loop is basically traversing diagonals which are at 135 degrees. If I is on the x-axis and j is on the y-axis, and the outer loop is basically enumerating each of those diagonals at a 45-degree angle. And notice that all the dependencies are basically at the 135-degree angle, and so the outer loop can be fully parallel. But that's a very kind of that this method of identifying parallelism only works for kind of small programs and with only depth 2 loops which can be drawn in such a way and stuff like that. But I want a more general mathematical formulation, and we're going to discuss how we can do the transformation, how we can go from here to here, which means go from a loop which does not have parallelism at all to a loop that basically has parallelism, at least in its outer loops, if not in the inner loops. And also we talked about how it's not just about parallelism, but it's also about locality. By basically clustering all the dependencies, accesses in the inner loops, we are basically reducing the reuse distance between data dependencies, and that basically improves locality. But here, I want to basically have a better mathematical grounding on why I say that the outer loop is a parallel for loop, whereas the inner loop is not a parallel for loop. And the answer is basically the fact that we can prove that there are no data dependencies across different values of k. Notice that the outer loop, basically different iterations of the outer loop will have distinct values of k. For example, k equals 0 versus k equals 1, or k equals 10 versus k equals 100, or something like that. And so I can prove that if k is not equal to k prime for two different values of k, then the two bodies will always have different locations that they will access, or in other words, there will be no data dependency. Now, what are the conditions for data dependencies? At least one of the axes should be a write, and then the addresses should be the same for some dynamic instance. And to show that, to basically produce, apart from the fact that there's should be at least one write, so in this case there is one write, and we are basically interested in data dependency across these two accesses. So I'm going to basically formulate that again as my mathematical system of equations and say, okay, this is my iteration space for I. So here I is basically formed by the iteration indices k and l. So I is basically kl. and vector I, and so bi plus b basically says what is the iteration space for k and l. So it's going to be something like between 0 and 1998 for k, and 0 and k minimum of k comma 1998 minus k for l. You may wonder how I am able to basically represent minimum in this linear form. Well, basically when I say L is less than equal to minimum of two values, this basically means I can have a conjunction. It says L is less than equal to K and L is less than equal to 1999 minus K. And so both of these are linear inequalities and can be represented in this form of Bi plus B. And so this entire iteration space indeed is a polyhedral space, and I can represent it as Pi plus B. And so I'm interested in two different iteration vectors, KL and K prime L prime, and I'm just representing them as I vector I and I vector I prime, such that Bi plus B is greater than equal to 0. B prime I prime plus B prime is greater than equal to 0. In other words, they belong to the iteration space, both of these values. Notice that I'm using I equals KL and I prime equals K prime L prime. And Fi plus small f is equal to F prime I prime plus small f prime. This is exactly the same thing that we had when we were talking about data dependencies in general. But I'll have one extra constraint now, which is K is not equal to K prime. And that basically says that the outer loop iteration numbers are different, right? Because for outer loop, K is going to be different. And so if K is not equal to K prime, I can now try to solve this using, let's say, an integer linear programming formulation. And once again, because I have not equal to sign, I would probably need two different ILP formulations, and we'll need to check each of them separately. But I'll basically, for this example, find that none of those formulations have any solution. In other words, this system of equations, this set of constraints, do not have a solution. And because they don't have a solution, that basically means for different values of K, the outer loop has no data dependencies, which basically means that the outer loop is embarrassingly parallel, and thus it can be parallelized without neither need for any synchronization. And so that's how basically we reason about why the outer loop can be parallelized, but the inner loop cannot be parallelized. I could have done the same exercise and replaced K is not equal to K prime with L is not equal to L prime, and I would get some valid solutions to the system of equation, which means that the inner loop cannot be parallelized. Okay, I should also point out, so there is no solution to the system of equations or this system of constraints, and so I am sure that the outer loop can be parallelized, and that's why I have the par keyword in the outer loop. I mean, in this particular example, I just showed the constraints between axis 1 and axis 2, which is the axis 1 is ak minus l comma l, and axis 2 is ak minus l plus 1 comma l minus 1. But I also need to similarly show no dependencies across dynamic instances of the same statement when k is not equal to k prime. So when k is not equal to k prime, this particular axis cannot conflict with itself, and similarly this particular axis cannot conflict with itself. So there are going to be more equations than what I showed in the slide, but all those equations are going to be of the similar form. Recall that when I check across the same axis, I also have the extra constraint that I is not equal to I prime. With all those constraints, I would be able to find that there is actually no data dependence between different iterations of the outer loop, and so the outer loop can be parallelized. So, and the constraint for checking that, for encoding that, is just k is not equal to k prime. Okay, so notice that this loop has an outer loop which can be parallelized, but the inner loop cannot be parallelized, and we say that this loop has 1 degree of parallelism because there is only one level of the loopness that can be parallelized, and so then thus we say that it has 1 degree of parallelism. In general, a loop nest has k degrees of parallelism if it has within the nest k parallelizable loops. In my previous example, there was one parallelizable loop, the other loop was not parallelizable even though it was a 2-depth loop nest, and so it was a 1 degree of parallelism. If you have k parallelizable loops, then you have k degree of parallelism. Here's an example of a loop which has 2 degrees of parallelism. It's a 3-depth loop for I equals 0 to n, for j equals 0 to n, for k equals 0 to n, aijk equals aijk minus 1. And so for different values of I comma j, there are no different dependencies, but for different values of k, there are dependencies between these two axes. And so the top level loops here can be parallelized, but the innermost loop cannot be parallelized. Okay, so this one has 2 degrees of parallelism, which basically means that there can be order n squared threads in this particular example. Notice that for each point in the iteration space for I comma j, For different values of k, I'll need to have put them in the same thread. But for I equals 0, 0 and I equals 0, 1, I comma j equals 0, 0 versus I comma j equals 0, 1, they can proceed completely in parallel, because between them there are no data dependencies, because they will be accessing different elements of the memory regions. In general, if there is k degree of parallelism and each dimension is basically iterating on average across n elements, then you have order n to the power k parallel threads, or we also call them virtual processors. So maybe the number of processors that I have are not going to be order n square, where order n square is a very large number. It could be million, billion or something like that. Or maybe the number of processors, physical processors that I have are only, let's say 100 or 200 or maybe even 10, 5 or something like that. And whatever is the number of processors, we basically map these virtual processors on these processors any way which we like. So our job as a compiler just finishes at basically creating as many virtual processes or process as possible, and then it's the job of the operating system's runtime to basically map these virtual processes to the physical processors. Now, how do I map these iterations to processors? Already I've discussed that the number of processors, virtual processors or processes that I can create is basically order n to the power k. So that's a lot of processes. And so you can think of this as a mapping function from the iteration space, which recall is a polyhedral space, to the space of processors. And now in the space of processors, this is the space of virtual processors. So I can actually have an unbounded number of virtual processors, and I say let the processor space also be a k-dimensional space. So just like my iteration space in my polyhedral space is an l-dimensional space, where l is the net depth of the loop. I'm just using L for the depth of the loop nest. Then if the loop was had k degrees of parallelism, then the processor space would be k dimensional. And so the number of points in the processor space would be n to the power k. The number of points in the iteration space would be n to the power L. And then there will be a many-to-one mapping from the points in iteration space to the points in the processor space. Why is this a many-to-one mapping? Because it is mapping a larger domain to a smaller range. L is greater than k, of course, because k is the number of parallel loops, L is and L is the total number of loops in the loop nest. So it's a many-to-one mapping. And so we are interested in finding this mapping such that the data dependencies are respected. So irrespective of the given loop, let's say my original loop was the first loop that I had, which where the data dependencies were not apparent. We want to transform it. In one way to kind of model the problem is we basically want to find a mapping from points in the iteration space, let's say I comma j space, which is the iteration space, to processor space, such that I can basically use as many processors as possible. In other words, the range of the function should be as large as possible. So we want to identify such a function. Notice that this is a function. It's a many-to-one mapping, so it's a function. For every point in the domain, there exists a unique point in the range. It's not a one-to-many mapping. Okay, so so we are interested in finding a many-to-one mapping, and that's what I'm going to call a partition of the iteration space, so that every set of iterations is given to every single virtual processor. Maybe it's an embarrassingly parallel loop, in which case each iteration can be given to a separate processor. And if it's not an embarrassingly parallel loop, then a group of iterations will be given to a specific processor. And we are interested in finding this function, but we'll have one more constraint. And the constraint is that this function from the iteration space to the processor space needs to be an affine function. So notice that everywhere the common theme in this polyhedral analysis is that we are dealing with affine spaces, whether it be an iteration space, it is an affine, it is a polyhedral space, which means it is specified using affine constraints, whether it is memory access, those are affine functions on the iteration space. And similarly, the mapping from iteration space to process space, we are going to restrict ourselves to affine functions. Notice that this is a restriction that we are putting on ourselves. If we relax this to any possible function, we may be able to get a better solution. Maybe we may be able to get better parallelism. But then the problem becomes harder to solve. If the functions, we limit ourselves to affine functions, the problem becomes easier to solve. We will be able to solve them using integer linear algebra, just like we have been using integer linear programming earlier to solve such problems. And so we want to restrict ourselves to affine functions. Moreover, affine functions are actually, are a pretty large category of a rich set of functions. So it even like just this restriction is not really going to hurt us in most cases. Moreover, because we are already talking about only affine programs, an affine function usually is good enough for extracting the maximum amount of parallelism, although not always. Okay, so here is an example. Let's say the other thing I want to point out is that it's not necessary that if the original loop put some statements in the same iteration body, in the transform loop it is going to be in the same iteration body as well. So here to motivate that, let's say I have a loop for I equals 0 to n, ai equals 0, bi equals 1. Now these two statements have no data dependency with each other, right? Because they are accessing totally different locations. One is accessing the array A, one is accessing the array B, and so on. And so they have no data relation, and they are no data dependence. They are completely independent. And so it should be possible for my, if I say what is the maximum amount of parallelism that I can extract from this program? Well, one answer is that each of the iteration points can be parallelized. So I can have at least order n number of virtual processors, each processor basically doing one iteration. But actually I can do order 2n, because I can have I can have the first statement ai equals 0 executing in parallel with the second statement bi equals 1. And so actually I have 2n different virtual processors for this particular loop, and our formulation of the problem to find parallelism in a loop should be able to exploit this fact that there is no data dependency across even within a body. So it should be able to split the body. So for example, it should be able to do the following. It should be able to create two parallel for loops, one which is doing ai equals 0 and the other which is doing bi equals 0, and all these 2n threads should execute in parallel. I should point out again that when I say a statement, I'm basically talking about every access as a statement. In other words, it's a 3-address code statement. If you recall, when we're talking about intermediate representation, we're talking about 3-address code. So it's, a memory access is a 3-address code statement. It's not the C statement or something like that. And so when we are doing this analysis of parallelism and locality, each 3-address code statement, in other words, each static access is going to be analyzed separately so that we can exploit the maximum parallelism. In this case, this is one 3-address statement, ai equals 0, and bi equals 1 is another 3-address code statement, and we're going to analyze them separately, and our best solution is going to be this, and hopefully our formulation of the problem is going to let us arrive at this best solution. So to conclude the discussion, the space, when I say iteration space, this was actually, I should qualify it, it's the iteration space of a single statement S1, where S1 is a 3-address code statement. And similarly, there could be another iteration space for another statement S2. And once again, we'll have, and the processor space is common. And for S1, there could be some function. And for S2, there could be another function that is mapping the iteration space to the processor space. Both of these can be many-to-one mappings, and will likely be many-to-one mappings, or they could also be one-to-one mappings. And both of these will be restricted to be affine functions. We are interested in finding affine functions for each of these mappings such that they maximize the total number of processors that are getting used. And we're going to discuss algorithms on how to find such an affine function in our next few modules.